We were looking at Buckingham Pi Theorem in the last class. Let's just go through it once again so that you get it straight. So we really did not complete the theorem that day. So let me just state the theorem. So what we did is we actually tried to do an example. So what it says is that if a physical process involves n variables which contain j dimensions, then a relationship containing k non-dimensional variables can be written down and k will be greater than or equal to n minus j. Okay. So suppose you have a physical process which contains, let's say, n variables and it involves j dimensions, then you can find a k which is n minus j or greater than n minus j, and you will be able to find k non-dimensional groups and you will be able to write down a relation between them. So the problem that we had was some object with a characteristic dimension L and a fluid approaching it with a velocity u and has the properties density rho and viscosity mu, and you were interested in calculating what is the force exerted by the object on the fluid, and you said that's actually going to be a function of u, L, rho and mu. And we said we have identified now 5 different variables and we will write down the dimensions of each of them. So force has the dimensions of mass, length, t to the power minus 2, u is L, t to the power minus 1, L is L, rho is m, L to the power minus 3, mu is m, L inverse T inverse. Okay, so that means we have identified n is equal to 5, j can be 3 because it's mass, length and time, and therefore we should find k which is equal to 5 minus 3, 2 non-dimensional variables that we should be able to identify. And then we said that we have to select the repeating variables first. So j repeating variables which we chose as length, u and rho, and therefore we wrote down our first combination pi 1 which contains f times L to the power a, u to the power b, rho to the power c, and in terms of dimensions we wrote that as m L t to the power minus 2 times L to the power a, L t to the power minus inverse x powered by b, and m L to the power minus 3 to the power c, and we said that has to be equal to a non-dimensional number, that means I should have m to the power 0, l to the power 0, t to the power 0, which means if I equate powers of m, powers of l and powers of t, I am going to get 3 equations, and if I solve each of them, I am going to get the numbers for a, b, c, and therefore it came out to be f divided by rho u square l square. That's what we had done last class, right? All of you back on track? So then we can talk about the next parameter. So the second non-dimensional number pi 2 can be generated with mu. Mu is the other variable that we haven't taken care of yet, times L to the power A and then U to the power B and rho to the power C. So that means in terms of dimensions, that's going to be m L to the power minus 1 t to the power minus 1, that's that of the viscosity, times length, length to the power a, velocity L, t to the power minus 1 to the power b, density m, L inverse, L cube to the power c, and we will insist that that has to be a non-dimensional number. Therefore, I can equate the dimensions of each of them. Equating the dimensions of L would give me 1 plus C is equal to 0 or C is equal to minus 1. Equating the dimensions of time, I get minus 1 minus B is equal to 0. That gives me B equals minus 1. And equating the dimensions of length, minus 1 plus A plus B minus 3C is equal to 0. So that can give me, which is the one that I don't have, A is equal to 1 plus 3C minus B is equal to 1. C is minus 3 plus 1. 1 plus 1, 2 minus 3 equals minus 1. And therefore, pi 2 is equal to mu times L to the power minus 1, U to the power minus 1, rho to the power minus 1. But that's nothing but mu divided by L U rho, which is nothing but inverse of Reynolds number. Okay. So, we have identified therefore pi 1 as f by rho u square L square, pi 2 as, I'll just write it as mu by L u rho. Buckingham Pi Theorem says that there exists a relationship between pi 1 and pi 2, which you simply write as f by rho u square L square is some function of Reynolds number, which you do not know what the function is, but you have identified the non-dimensional variables. Okay, so that's the quantity that you get just by analyzing the dimension. So this is one way of doing it. Okay, there is another way of doing it, okay, which is relatively simpler and is known as Ibsen's method. So in this case, we will look at the same problem and try to derive the same relationship, but in a slightly different procedure. We will write, we want to get force, okay, as a function of what all things L, U, rho, mu. That's our intention at the moment. The first thing that you do is again write down the dimensions of each of them. Force has the dimension of m, L to the power L, t to the power minus 2. Length has the dimension of L, U has the dimension of L, t to the power minus 1. Rho has the dimension of m, L to the power minus 3, mu has the dimension of m, L to the power minus 1, t to the power minus 1. So, in this method, what you have to do is you have to systematically eliminate dimensions. Okay, so what you should do, Ibsen's method says that systematically eliminate dimensions. That's all it says, which means this eliminate. Okay. We have got mass, length and time. Let's say we decide to eliminate mass first. So, if you want to eliminate mass, what you can do, you can select a variable which contains mass and then divide appropriately. For example, in this case, let's say we have mass in force, density and viscosity. We can select any of them. The simplest is probably density. So, I will use density to eliminate mass from all variables that contains mass dimension in it. In other words, I will divide f with density, I will divide mu with density. Okay. So, if I do that, I will write f by rho is going to be a function of L, there is nothing that you need to do, U, nothing you need to do, rho by rho is 1, so I will not write it as any more a function of rho, and then mu by rho. So, what have I done? I have actually divided each of the variables, okay, which contain mass with density, so that mass goes away from the description. In fact, if you look at it, the number of variables are still same. It contains f, rho, L, U and mu. I have not removed density from the problem. Density is still there, but I have written it in such a way that instead of telling force, I will talk about force per density. Instead of talking about viscosity, I will talk about viscosity per density. The problem still contains 5 variables, but it's now written in such a way that the sum of the combinations don't have mass in it. Is that clear? So what is the dimension of f now? We originally had m L to the power t minus 2 and I have divided with density. So, that's L t to the power minus 2 m divided by m L to the power minus 3. So, the dimension of f by rho is L to the power 4 t to the power minus 2. L is still L, U is L t to the power minus 1. Mu by rho is, we originally had m, L inverse, t inverse. I divided with m, L to the power minus 3. And therefore, I ended up with L square t to the power minus 1. Okay, yeah. Because there is no m in it. Okay, so I am not dividing the expression. I am dividing the variables. So, instead of talking about force, I will always talk about force per density. Okay, so length has nothing to do with it. So, I just keep it L. Okay, remember we are not dividing the expression with density. Okay. Okay. So now this expression, if you look at, this expression has only length and time in it. I can choose to eliminate length or time. Okay. So, let us say we do time first. So, let us eliminate time. So, if I want to eliminate time, I could use L, U or mu by rho. I will eliminate t by dividing with u, let us say. So, that means I had f by rho which contains, whose dimension is now L to the power 4 t to the power minus 2. So, if I want to get rid of t to the power of minus 2, I should divide it with u square, so that I can get rid of my u. So, sorry, t. So, I will do f by rho u square is a function of L continues to be there L. I don't have to care about U now because I'm going to divide U with U, and 1 density is anyway not there, comma mu divided by rho. I have L square t to the power of minus 1. So, if I want to get rid of time, I just need to divide it with U, right. So, now if you look at f by rho U square, originally it had L to the power 4 t to the power of minus 2. I have divided it with U square. That means I am dividing L to the power 4 t to the power minus 2 with square of that, and the only thing that is left out now is an L square in it, right. F by rho U square has the dimensions of length square. Length continue to have length. Rho U was originally L square T inverse. I divided with U, and therefore the only thing that is left out is a length in it. Yeah. Okay. So, now the entire expression only has length in it. I can now eliminate L, and to eliminate L, I will use my length L itself. So, I can divide L square on the left hand side. F by rho U square L square is a function of mu divided by rho U L. Okay. So, we have ended up with the same conclusion that we had from the previous procedure. So, the good thing is that here you don't need to solve, the algebraic equations. You don't need to really identify, how many, you don't need to figure out what are the repeating variables and so on. It sort of comes out naturally. Yeah. I didn't understand. Can you explain again? Yes. No. So, J is 3. So, you will get 2 non-dimensional variables. N minus J non-dimensional variables. Then you will get 3 non-dimensional variables. So, and see this we have, so for example, here you have f by rho U square L square is only a function of another non-dimensional variable, right. So, similarly, if you have 3 of them, you will find pi 1 is a function of pi 2 comma pi 3. You don't know what f is, but this is the best you will be able to write. So, originally if your problem contained 6 non-dimensional variables, let's take the same situation. Let's say, so you only asked last time probably that if the shape was different, let's say that it has a length L and let's say a width W. Let's say the third dimension is also W. Then our f is going to be a function of L, comma W, comma rho, mu, U. So, here n is going to be 6, okay. But in this case again j is going to be 3, okay. So, you can expect to find 3 non-dimensional variables, okay. Let us say you will find out them as pi 1, pi 2, pi 3. Then you can say that this is what the relationship going to be, and so on. What would be the extra non-dimensional parameter that will come in this case? Can anybody guess? It will be just W by L, okay. Everything will remaining same, right? You only have an extra W, okay. So, W by L is the extra parameter that is going to come in, which is basically the aspect ratio of the body, which is a non-dimensional parameter. And that is so simple in this case because we have added just something which has a dimension of length and something physical. Okay. So, that is fine. So, we have now learned how in a given problem, if you are familiar with the number of variables or the number of variables that could be relevant, then you can write down a simple relationship instead of investigating the dependence of each of the variables. Okay. So, now if you look at the flow, what did we do? Initially, we said if we knew the relation, how to non-dimensionalize the variable, So we did it using an algebraic relation. We also did how to deal with the differential equations. Then now what we have done is, we did not know anything. We only knew that these are possibly the variables that are affecting, and then we have written down a relation. Okay. So one of the crucial things, okay, that you have seen in this step is that you can write down the dimensions of any physical variable as a power law expression. So I mentioned it a few classes before, that we have written down the variable, any variables, the dimensions as a power law expression. Okay. So is this always going to be the case? Can we always write the dimensions as a power law expression? And we are going to prove that yes, it is possible, and therefore all the things that we have said so far will continue to be hold for any problem that you pick up. Is the objective clear? Okay. Consider a variable, let's say x, okay, which I'll write as xu when I have chosen a unit system u. So what is that? I have chosen a unit system u in which x is some variable, okay, and the small x is therefore the magnitude of that quantity. Okay, x is some physical variable. For example, it's like F is equal to 10 Newton, force is equal to 10 Newton. That's all what I have written, but in a general form. Okay. Or I could write this as x prime u prime if I select a unit system u prime, or x double prime u double prime if I select a unit system u double prime. So what I am saying, maybe I will take my SI system or CGS system or MKS system. I could always write it, right? So for example, if it's length, I can write it as 1 meter, 100 centimeter, anything that I like. So that's what I have written now. And we know that all these should be related, right? All these will be related by some factors. For example, x prime by x will be some number, right? X prime is the magnitude in a unit system, x is a magnitude in some other unit system, and they will be related by some number. So similarly, x double prime by x, for example, these are called reduction ratios. Reduction ratios are nothing but the numbers that you need to multiply when you are moving from one system of units to another system of units. Okay. Let RL prime, RM prime, RT prime be the reduction ratios for length, mass and time. Okay. So when I define my x, I did not say what it is, it's some variable, okay, some physical variable. This is better. And you know, RL prime is, for example, the reduction ratio for the length. Okay, when I am changing from unit system u prime to unit system u, what is the number that I should be multiplying with? Okay, that is RL prime if I am talking about length, or if it's mass, let's call it RM prime If it's time, let's call it RT prime. Okay. Similarly, so then I know that I can write x prime by x is going to be some function of RL prime, RM prime, RT prime. Okay. So, the reduction ratio for length, reduction ratio of mass, reduction ratio of time, each of them if I combined in some form, I should be able to get the reduction ratio for any other quantity that I am dealing with. Remember, I am only worried about 3 dimensions now, okay, 3 particular mass, length and time only, okay. As you expand the problem, you could have other things coming into the picture. Similarly, I could write x double prime by x is a function of RL double prime, RM double prime, RT double prime, where RL double prime, RM double prime and RT double prime are the reduction ratios when you are going from a unit system of U double prime to a unit system of U. Okay. Then I can write x double prime by x prime is equal to f of RL double prime comma RM double prime comma RT double prime by f of RL prime comma RM prime comma RT prime. I just divide the two equations. This is 1 by 2. All right. Now, how about quantities RL double prime by RL prime, RM double prime by RM prime, RT double prime divided by RT prime. So, those are the reduction ratios when I am going from a coordinate system of U prime to U double prime, right. So, these are nothing but reduction ratios when we go from U prime to U double prime, which means I could also write this expression, which is when I am going from x double prime, sorry, if I am talking about x double prime by x prime, that's also is a function of RL double prime by RL prime, RM double prime by RM prime, RT double prime divided by RT prime. Do you agree? So, what have I written really? See, if you look at the right hand side, I take the reduction ratio for length, mass and time separately and combine them. Or if you look at the expression in the middle, this part, okay, I calculate the quantity in two different units and then take the ratio, then I am going to get the same thing. For example, if I am talking about force, okay, I calculate, so this part, let's say the double prime, okay, is I have calculated it in some units, okay, let's say mass into acceleration I have done, let's say I have done it as kilograms times meter per second square, or this quantity, the one in the denominator, I'll do it in CGS unit. Let's say I'll do grams into centimeter per second square. If I do the force ratio or I do the mass ratio and acceleration ratio and multiply them, the answers are going to be same. Essentially, this part is just that fact that whether I do the forces and take the ratio, or if I take the each of the components mass, length and time separately and then take the ratio and do combine appropriately, I am going to get the same expression, okay, or same ratio, same number. That's what we have. Okay, any doubts? What we will do is we will fix u double prime and change u prime arbitrarily. So far I talked about fixing an system. I am saying that one of the system I am going to fix, the other one I am going to consider to be a variable, so that I can do differentiations and integrations and so on. So I will say that in this quantity, in this boxed expression, I am going to keep my double primed variables as fixed quantities and my primed variables as really variables, so that I can do differentiation. In fact, what I want to do is I want to take partial derivative of, let us call this expression 3 with respect to, let us say, RL prime. Okay, so I am keeping my primed variables as variable really. So if I differentiate it, so I'll do the other way. Okay, I'll keep the u prime. I'll keep u prime as the variable, as the fixed quantity, and u double prime as arbitrary, so that I can differentiate the primed variables. You could do it either way. You'll see that it's just inverse of another. So I have to now differentiate this boxed expression with respect to RL double prime. So the numerator is a function of RL double prime. So I should differentiate it. The denominator is not a function of RL double prime. So I don't have to do anything. The right hand side is a function of RL double prime by RL prime. So I should be applying the chain rule. So let's do that. So the left hand side comes out to be dou f by dou RL double prime, which is could be a function of RL double prime, RM double prime, RT double prime, divided by the numerator was a constant RL prime, RM prime, RT prime is equal to partial derivative of the right hand side with respect to this variable. So that's going to be dou f by dou RL double prime of RL double prime by RL prime, RM double prime by RM prime, RT double prime by RT prime divided by RL prime. I just differentiated it. Okay, so because the variable here is really RL double prime by RL prime, so it's a derivative of f with respect to that times the derivative of that quantity. Okay. Now, having done that, let RL double prime approach RL prime. Okay, we are changing RL double prime, it's a variable. Let's say that we are actually going to change it, okay, such that it is going to become the primed variable itself. Okay, so that I can replace all my double primes with my primes. It's like, see, I had a variable y and I had another variable x. I kept my y fixed, I had my x changing. I'm saying that now I'm going to keep my y is equal to x. I'm allowed to do that, it's just a function. So I just do that, in which case this quantity is nothing but dou f by dou RL prime of RL prime, Rm prime, Rt prime divided by f of RL prime, Rm prime, Rt prime is equal to dou f by dou RL prime of 1, 1, 1 divided by RL prime. So I'm really putting the double, yeah. So which one did we keep? We fixed u prime and changing, no, I am changing my u, fixing my u prime and changing my u double prime. So u RL double prime basically approaches RL prime. Is that what I have written? Yeah. All of them, all of them. In fact, what we are doing is we are actually approaching, changing our u double prime into u prime. You had some doubt, somebody? Okay, so that's what we ended up with. If you look at this, this is some derivative, okay, evaluated at a constant. I'll just call that alpha for the convenience. Also, this is really a function of primed variables. I'll just drop the primes now onwards, dropping primes. Okay, I'll just write it as dou f by dou RL, a function of RL, comma Rm, comma RT by f function of RL Rm Rt is equal to alpha by RL. That's what we ended up with. Okay. Now, I am going to integrate this quantity, integrate this expression, okay, with respect to RL. Actually, not right. I am just integrating the quantity, integrating the quantity. Okay, so that I can write this as df as a function of RL, Rm, Rt divided by f of RL, Rm, Rt is equal to f of DRL divided by RL. Just rearranging, okay, and doing the integration. So this is dou f by dou RL. I'm keep bringing this DRL to the right hand side and integrating. That's all. And what do I get? Log of f RL Rm Rt is equal to alpha times log of RL plus a constant. I have been doing things only with respect to RL. That means I have kept my Rm and Rt constant. So it could be actually a function of Rm, comma Rt. That's the integration constant that I will have. In fact, I'll just write it as log of that, so that I can write f, which is a function of RL, Rm, Rt is nothing but RL to the power alpha g of Rm, Rt. Okay. So this is what I get if I do it with respect to L. But you can see that this L was just one thing that we chose. We could do this with respect to M, and we could do this with respect to T, which means I am going to end up with RL to the power alpha, Rm to the power beta, Rt to the power gamma. Right? Just repeating the differentiation with respect to Rm, Rt, etc., and then performing the integration. You can do it and you will find that there is nothing that's going to change. L was just an arbitrary choice. What have we really done? We found that f of RL, Rm, Rt, some function of reduction ratios, is just going to be a power law expression. Okay, that's what we found. Reduction ratios are the ones which you will use when you are changing from one system of units to another system of units. We started by saying that we are going to look at a quantity x, which we will write it as either xu or x prime u prime or x double prime u double prime and so on, and we said we are looking at quantities like x prime by x, x double prime by x and so on. Okay. Now, if you want if the reduction ratios are going to be power law expressions, then the only way x can be, x has to be having a form L to the power of alpha, m to the power of beta, t to the power of gamma. If x has the form of L to the power of alpha, m to the power of beta, t to the power of gamma, then only I can have my reduction ratio having, the reduction form will basically have this power law expression, right? If my x had any other form, okay, not just this power law form, anything else, then my reduction ratio cannot be like this, because reduction ratio is by definition when I am going from one system of units to another system of units. So, any x that I choose, if the dimensions do not have this form, then I cannot have this form of reduction ratio. So, now we have found that the only way, in an arbitrary case, the reduction ratios will always have a power law expression. That means dimensions will always be power law expressions for any physical variable that we choose. And you have seen that, right? Any system, any unit that you write will always be something to the power of something. It's never in any other form. Okay, that's what we have proven now. That has to be the case always. Doubts? Yeah. Sure. Here? Oh, this was my equation, right? Dou f by dou RL prime. So, the only variable that I have is RL prime. So, I just drop that R primes, or you could just continue writing everything and you will end up with an expression saying that f of RL prime, Rm prime, RT prime is RL prime to the power alpha. So, there is no physical this thing there. Yeah. Which one? RL prime. Should I go up? No. Oh, it's general. Yes. Can you be loud? No, it can't. No, because by definition it contains only length. It's like 100 centimeters. It could be when you are going from CGS to SI, RL prime is just 100. Like that, okay. It does not contain by definition mass or time. Mass and time are fundamentally different dimensions. So, therefore, RL prime cannot be a function of Rm or RT. However, x prime could be. I mean, we wrote it as x prime by x, which for example could be a reduction ratio for force, which means it will contain both length, mass and time in it. So, what we have done is either we write it as a combination or we write it separately. That's what we did, and that's what exactly that boxed expression was telling. This red boxed expression, that on the right hand side, I do it as a function of I'll change all the lengths, I'll change all the masses, I'll change all the times and appropriately combine it. Or on the left hand side, I'm saying that okay, I'll take the force in one unit, I'll take the force in other units, and I'll take the ratio of it. I'll get the same number. Go down. So far till we got this expression, we kept these two things as two different units, RL prime and RL double prime, or rather U prime and U double prime as two different units. Now, I am saying that one system is up and we kept one of them fixed and other changing so that we could do a differentiation. Now, we are saying that the one which we are changing is actually approaching the one which we have kept fixed. Okay. So, therefore, each of these ratios RL double prime by RL prime is essentially just one number. I mean, it's basically same quantity, because U double prime and U prime are the same system of units now. Okay, so there is no reduction ratio really. That's why I just wrote it as 1, 1, 1. Or simply you say that I am going to say my RL double prime is equal to RL prime, and so on for all primed quantities. And that's why it's a constant, and you can see that that constant is what comes out to be as a factor, which says that the quantity is that that comes as powers is essentially the derivative with respect to that unit system. That's what that power means. Okay. So you go back, you revise all these things. The proof is not very important. The proof is there because I thought it's a nice thing to do. You can just learn it, and more important is to learn how to do the problems. We'll do one more proof, and that's we are going to prove the Buckingham theorem. So I just said that if you have n variables and j dimensions, then we will have n minus j non-dimensional parameters, right? So we'll again do a similar proof like that, and then we will wind up this topic. Okay, I'll see you tomorrow.